Hi everyone, today I'm going to talk about gold. So gold is located at group 11 with same rows as with copper and silver, and it is located in period 6. Its atomic number is 79 and it is solid at room temperature. It is a transition metal. It is also a face-centered cubic (FCC). It has a lattice constant of 4.07825 angstrom. For applications, gold is noble metal which famous for its stability against rust, tarnish, and chemical corrosion. Although conductivity not as good as silver and copper, but silver and copper conductivity will degrade after rust to become copper oxide or tarnish to become silver sulfide. It is commonly used as PCB exposed contact point as shown in this two picture, and also used in wire bonding in IC packaging, which join the IC chip and the lid. For characterization, the first one is XRD. We can see here's the XRD diffraction pattern of gold. Here we focus on the first three planes. So it's a 111, 200, and 220 plane. Here I have screenshot and put. So this is the image of the 111 plane and 200 and 220. They are highly arranged in order to produce diffraction pattern on the screen. So we can see here they are arranged in order. So here is the formula shows that we can use this formula to calculate this distance between the planes. For example, here we can see the plane here. So I have listed out, I've added the plane, these three planes, so we can see clearly how the plane looks like. So the D, just now the formula D is for this, the distance between these two planes. And A is the lattice constant, which is the distance between this atom and this atom. It's also the length of this cubic. We also see for the 200 plane. So this is the 200 plane. So the formula calculated the D between these two planes. You can see here, slanted a bit to see the plane. So we can compare this, the distance between these two planes. Of course, the 111 will be a larger distance because the theta is also smaller, right? For the Bragg's law, we can see here if the D is larger means the theta will be smaller. So a smaller theta will have a larger D. So 111 have a larger D. We can conclude here. So we take the 220 plane and take the 111 and we can compare here. Also we can see roughly the distance of 220 is more smaller than the 200. So we focus on 220. You can see this is a plane that forms the diffraction pattern. For 200, it is this plane, and then for 111, it is this plane. So back to the slide. Now I have screenshot all the plane diffraction pattern in here so we can see easily. So now let's look at the comparison between gold and silver. So we can observe here they are both similar, and except the 2 theta is shifted. So we can see here, for example, at the 80, we can see the peak is just over the 80 for gold, and for the silver it is shifted to the right side. So what we can conclude here is their lattice constant is different. So we take one plane as example. So let's say the 111 plane. So this HKL is a constant. So what we change is the A. For example, the silver is 4.10 and the gold is 4.17. So as go from gold to silver, the A is decreases, so D also decreases. So at the Bragg's law, the D decrease, so sine theta will be increased. So theta is increased because the n lambda is constant due to the X-ray is constant. We measure using the same wavelength. So as theta increases, the peaks will be shifted right side. So the silver peaks is all shifted right side with a certain ratio. So comes to a TEM, transmission electron microscope. So I can show here. So here is the TEM simulated TEM diffraction pattern. So we can see the black screen here. It shows the pattern diffracted on the screen, and also its reciprocal space in the right side screen. So I want to show a famous thing here is about the reciprocal space of FCC is BCC. So we can see here when we turn the cubic crystal cubic, the right side screen shows the pattern diffracted out. But what we see is not face-centered cubic, it is a body-centered cubic. So this also proves that FCC's reciprocal is BCC. So I also have the example from the paper of the high-resolution TEM. So for the first picture A and B, B is the enlarged version of A, so goes to C and D. D is an enlarged version of C. So the B showing that the 001 family, which is the pattern like this, and I also screenshot the plane. It looks like it's like this. And for the D, it is a 110 family. So this is the plane I screenshot. It looks like this, and also similar at here. So this is the billowing zone of FCC. This is some label on the billowing zone. This is only a part only because if we turn to other direction, it is also a replicate of this type of axis. For the phonon dispersion, this graph I taken from one paper, and the dotted line is represent the experimental data. It is performed using inelastic neutron scattering (INS) using triple axis spectrometer (TAS). For the line, it is theoretical calculations, for example, force constant model or density functional theory (DFT). So we can see the theoretical and the experimental is matched quite well. Before that, we need to know what is x-axis and y-axis represent. So for x-axis, it is a wave constant k, which also equals to 2 pi over lambda. Here the x-axis is actually reduced, so it is k over k max. K max is equal to pi over a, so means a equals to lambda over 2. So for y-axis is energy, but it converts from neutron kinetic energy to frequency, then to wave number. They are converting using E equal to hv formula. For gold, it has only 3 acoustical branches, 3p, and p is equals to 1 because the primitive cell is 1, because it is not like NaCl have 2 different atoms. It has only 1 atom, which is Au, so it has 3 phonons in total. 3 acoustic by default is 1 longitudinal acoustic and 2 transverse acoustic, and then with the formula 3p minus 3 is equals to 0. This shows that it no optical phonon. Let's see the comparison for copper, silver, and gold. From the graph, we can tell that all are similar because all is also FCC, and the most obvious difference is the energy they obtain. So because of the mass of the gold is larger than silver and silver larger than copper, so because gold is heavier, so the vibration frequency is also lower, so it has a lower energy compared to silver and copper. For electronic band structure, this shows that because of overlapping of the conduction band and valence band, so they have no band gap, 0 EV, and also no direct or indirect band gap. Then it also is a metallic, so it conducts electricity. Now for UV-Vis, ultraviolet visible spectroscopy. For gold, UV-Vis is suitable for identifying nanoparticle size of gold powder. So we can see here they have different variation of nanoparticles of gold powder. They have minimum 20 nanometer until 400 nanometer. We can see the curve here. The smaller the nanoparticle, the curve is more obvious. And then for the 400 nanometer, the curve is very flat. So this UV-Vis can identify the nanoparticle size of gold powder. Here's my reference. Thank you everyone.